Welcome back. So we are going to discuss now part 2 of linear combinations. And in particular, we are interested in making the connection between this definition of linear combinations of vectors and linear systems of equations. So we had previously spent a little bit of time in learning how to compute or calculate the solution set of a system of linear equations. And now we're revisiting that type of endeavor, but we are doing so by means of expressing first the system as a linear combination. So one thing to notice is that we're going to use a so-called column partition. We're going to think of the matrix A, okay, partition into columns A1, A2, all the way through A sub n. Okay, this is the column partitioning of that matrix. The other way of thinking of this, which is sort of my one way I'll keep using throughout, is thinking of the matrix A as a rectangle, and such that this matrix has a little of these vertical bars here. Okay, a lot of these vertical bars, and each of those, the first one is called A1, the second one is called A2, the next one is called A3, all the way until you get to the end. This one is called A sub n. So each of those vertical bars is a so-called column of the matrix. So we're going to think of the matrix of coefficients A, and in particular, we're going to think of the columns of the matrix of coefficients. Remember that if this is the matrix A, we're really interested on the column partitioning, such that the this goes from column 1, A1 through AN, and then we stack there the vector of constants, which is B, and that would be the so-called augmented matrix, which we need to row reduce in order to find the solution set. But the other thing to note is that this theorem establishes the solution of this linear system. The solution we find by row reducing this matrix is in fact a linear combination. X is a solution if and only if B is equal to the linear combination of the columns of A, such that the entries, those values stored in every location in X, such that those entries are indeed the scalars on that linear combination that equals B. In other words, we consider a so-called solution if those values of that solution can be used as scalar values in this linear combination, such that we have a vector equation. So here is an example. We have 3 equations, 4 variables. We form the augmented matrix. This augmented matrix row reduces to this RREF. Clearly, with this information here, clearly R equals 2. In this case, N is 4. There is a row of non-zeros. N minus R is not equal to 0, so that is implying that the solution set of this system is going to have infinitely many solutions. There is no 1 in the last column, therefore the system is consistent. It's a lot of information, right? So what we're going to do is we are going to go on to this business of writing the solution set, for which we need the set D, the set F, and we note here that D contains indices 1 and 2, F contains indices 3, 4, and 5. We are not going to make use of 5. The free variables would be x3, and x4 are going to be considered the free variables. So we're going to express x1 and x2 in terms of x3 and x4. And then we do so by reading the information from the RREF, right? So we know how to translate the first row of this is telling us that x1 plus 0x2 plus 3x3 minus 2x4, this equals 4. And so we can easily solve here for x1, and that gives us 4 minus 3x3 plus 2x4. Okay, and we can do something like that from the second row. So that leads to these expressions, and then what we really want to stress now is how we write this solution vector, this vector with entries x1, x2, and x3, where entries x1 and x2 are expressed in terms of x3 and x4. We're going to write this as a linear combination. So we can collect all the terms. There will be a 0 here. We can collect all the terms that contain x3. We can collect all the terms that contain x4. We can think of this as 0 plus x3. In fact, 0 plus x3 plus 0 x4. And this here, this is 0 plus 1x4 plus 0x3. So if we think of that in that way, so we can represent this vector as the addition of these three vectors, and in fact we can work, say this vector here in the middle is 0 times x3, which means we can write this as a linear combination where the coefficients x3 and x4 are indeed the free variables. So what we want to go is, what we want to do now is to outline an algorithm, a method that we can apply to any solution set of any system of equations. So the method would be step 1, write the vector of variables as a fixed vector. The fixed vector is what we call a fixed vector here is the vector that doesn't have coefficients multiplying in front of it. The vector is not being multiplied by anything. So this is what is typically called a fixed vector. Okay, so we're gonna write the vector of variables as a fixed vector that is added, that is being added to a linear combination, and the number of vectors in the linear combination is n minus r vectors. And so using the free variables as the scalars in that linear combination of n minus r vectors. Step 2, well, this is step 1 in this particular example. So we write these vectors indicating with some blank entries over there, and keeping in mind that each of these vectors has 4 locations, right? In this case. So then we're going to write zeros and ones. We're going to write, for example, a 1 in the corresponding location for each of the free variables. So there will be a 1 on location 3 here, and there will be a 1 on location 4. But there will be a, for this vector here, there will be a 0 in location 4, and for this vector, there will be a 0 in location 3. So we're going to substitute with zeros and ones to ensure equality in the entries of the vectors with indices in F. And that's what we do. And then we're also writing zeros on the corresponding entries of the fixed vector. And the next step is for each dependent variables. For each dependent variable, we're going to use the augmented matrix to formulate an equation expressing the dependent variables as a constant plus multiples of free variables. So we're familiar with this. Convert this equation into entries of the vectors that ensure the equality for each dependent variable one at a time. So this is explaining in so many words this process. So once we have an expression in which we have the constant that's on the other side in the last column of the augmented matrix, and we solve for that dependent variable, then we know these numbers, this coefficient minus 3 and 2, they are collected on the vectors that appear in the linear combination where x3 is a scalar multiplication, right? And this number 4 here is going to be put in the corresponding location, location 1 in this case, of the fixed vector. So we can do that for each of the dependent variables, and that's how we manage to fill in. See, there is a blank here, there's another blank there, there's another blank there. Those blank spaces will be filled in with numbers that come from this equation. Okay, so this expression. So this expression provides exactly the entries that we put on those locations that were previously blank. So all this is pointing to the so-called vector form of solution sets. This final form of a typical solution is much more useful. We can build solutions quickly by choosing values for the free variables and then compute a linear combination. So as an illustration, we select specific values. These are arbitrary values for free variables x3 and x4. So we set x3 to e2, x4 to e minus 5. You may try this with different values of your choice. They are free variables, right? And so then in this expression, what we do is to now replace the free variables exactly in this location. So we're going to write number 2 in that location, and then we're going to write minus 5 in that other location, and then we're going to carry on with the scalar multiplication operation and the addition of vectors, and that gives us one specific vector, which would be a solution among multiple solutions, a member of that solution set. We can give a try to other values of x3 and x4. Here's this for purposes of an illustration. So the solution set has certainly many members, but we can express the solution set saying that it's a solution is always going to be a multiple of this vector, minus 3, minus 1, 1, and 0, added to a multiple of this other vector, which it's also added to a fixed vector. So that's one way of thinking. So it only takes 3 vectors to describe the entire set, the entire infinite solution set. So this is a very powerful, these are very powerful ideas. And this theorem, vector form solutions to linear systems, something to review carefully. The notation the first time looks a little overwhelming, but note that what we have here are zeros, ones, and then entries on the RREF of the augmented matrix. Okay, so this is writing in a very formal way, a much formal way, a way of describing how to put together. But you really want to refer to the 3 steps that we outlined here: step 1, step 2, and step 3. We write this in much more formal notation. That's what this theorem is describing. The solution set therefore would be described as a linear combination plus a fixed vector, and notice that in this linear combination there are these many terms, and there are exactly n minus r of those terms, where r is the number of non-zero rows in the RREF and n is the number of variables.